this last video lecture of this section, we're going to talk about the peak shift effect. This is a really interesting effect, but let's go one step at a time. Let's first start with uh, drawing a generalization curve. So remember we had a response rate when we're drawing this generalization gradients. So generalization gradient. And let's use a different stimulus in this case. Let's use an auditory stimulus. Let's suppose we're talking about the SD being. The SD is going to be, let's say, 10 kilohertz tone. So this is in kilohertz. And then we have 8, 6, 4, and over here we have 12, 14, and 16, and so on. And so we got, because this is our train, this 10 kilohertz is our training SD, we're going to observe maximal response rate here, and as we go in one direction or the other, we should see something like, a sort of decline in responding, right? That's our generalization gradient. But notice one thing, one interesting thing, that we have this 10 kilohertz stimulus as our S delta, but we can, there's no, I'm sorry, our SD, our descriptive stimulus. Notice that there is no S delta. No stimulus that has been explicitly trained that it does not signal the reinforcement contingencies. We have one that signals the reinforcement contingency, that's the S delta, but we don't have a stimulus that signals the absence of, explicitly signals the absence of the reinforcement contingencies. Let's see what happens when we do that. When we do signal explicitly the absence of a descriptive contingency of reinforcement, we have to pick a stimulus. We're gonna say we're gonna use the 12 kilohertz tone as our S delta. I'm gonna try to make it as different as possible. So this is the one that signals the absence of the contingency of reinforcement. So the animal has been trained between these two alternating stimuli, SD, S delta, SD, S delta, 10 kilohertz, 12 kilohertz, 10 kilohertz, 12 kilohertz, and with 10 kilohertz, what that signal says, and the animal has learned this, is that pecking results in, or responding results in, a reinforcer, food, let's say. But with a 12 kilohertz, responding does not result in food. To a 12 kilohertz, the animal, so let's say this could be, this is on an maybe the SD, the descriptive stimulus signals the operation of a variable interval 30-second schedule. I'm just picking one just as an example. The S delta signals extinction. Responding does nothing. And you will see high rates of responding to SD, low rates of responding to S delta, to the extent that the animal can discriminate between 10 and 12 kilohertz. Not as an easy task. These two stimuli are very, very similar, but the animal may learn that discrimination if it has the auditory capacity to do it. So how would the generalization gradient look like? Would it look like this? That it's centered on the SD. That's the interesting thing. Most likely not. It most likely won't look like this. Let me erase this curve. Most likely, instead of peaking at 10 kilohertz, it's going to peak somewhere on the left of 10 kilohertz. Let's see, let's try to draw it as clearly as possible. It may look something like this, where it peaks maybe at 8 kilohertz, but not at 10. The peak of the distribution, or the peak of the generalization gradient that we saw that was before at 10 kilohertz, in the absence of this 12 kilohertz S delta, was shifted to the left because of this S delta. Even though even the maximum response rate may be at 8 or 6 or something like that kilohertz, even though reinforcement was never provided in the presence of any of those stimuli at 8 or 6 kilohertz. So why would that happen? Well, first of all, this phenomenon, the fact that you get this shift in the generalization gradient, is what we call the big shift effect. Now, the explanation of why this happens, the most likely one, it involves the sum of two generalization gradients, an excitatory gradient and an inhibitory gradient. Let's think about it. This is, let me erase this part. So this is, let me highlight it. This one that I'm making really thick is the observed generalization gradient. Okay? But the idea here is that there are two generalization gradients that produce this one. One of these gradients is an excitatory gradient. Let me erase this. Leave a little bit of space. The excitatory gradient that is centered around the SD. Maybe look something like this. This is the excitatory. Right? This is responses are well, let's leave it like that. This is the excitatory gradient. And now there's also an inhibitory gradient that is centered around the S delta. So notice that what we're doing is that what this is suggesting is that an is that an excitatory gradient is adding to response rate. An inhibitory gradient is reducing response rate. And when you add the two, you get the resulting observed generalization gradient. And so the reason why you don't see a lot of responding at 10 kilohertz is because even though you have a relatively high, you have the peak of the excitatory gradient, you still have also a pretty strong part of the inhibitory gradient. Whereas over here, at the peak of the observed gradient, the excitatory gradient is still strong, still high, and the inhibitory gradient is very weak. And that's why it peaks over here. All right. Try doing this with a numerical example. Try giving numbers to this, to the excitatory and inhibitory gradients, and then give positive numbers to excitatory gradient, give negative numbers to the inhibitory gradient, and add the two and see what kind of distribution you get. And most likely, if you pick the right numbers, um, you're going to see that the peak of the sum is not going to be, of course, at the it's not going to coincide with the peak of the excitatory gradient, but it's going to be shifted a little bit in the opposite direction of the S delta. All right, and this finishes our section on stimulus control.